In this module, we will learn about transduction a little bit more in detail. We will talk about how light is converted, transduced, into a language that the brain can understand, which is neural impulses. If you've ever gotten stuck by looking at a specific object because you were daydreaming or you were tired and you just stayed stuck looking and people were calling your name and trying to get your attention and you were just not in the zone, you may have noticed that you lost vision. In fact, it may have become blurry. In fact, if you try to look straight into an object right where you are, and try not to blink, and try not to move your eyes, try to be mindful of that. Little by little, the vision would become a lot more blurry. And the reason why is because our ability to continue to see depends on movements and repositioning of our eyes. And this is something that happens automatically. And this is what we call saccades. Saccades allow us, even though we're not aware of this in here, to continually scan the visual field. And our visual perception at any instant is nothing more than the addition of recent visual information. So our eyes continuously move even when we try to keep them still. These involuntary fixational eye movements are of three kinds. You have tremors, you have drifts, and then you have saccades. Please note that we are going to focus on saccades alone in here, and we'll also see how blinking serves a purpose. Although we are normally unaware of these eye movements that are typically occurring when our eyes are fixed, even if you're looking intently at a screen or somewhere, there are eye movements nonetheless. They have a critical visual function. When eye movements, or their main effect, which would be movement of the images on the retina, are blocked, the visual objects begin to fade or disappear. This happens because most of the visual neurons respond only to changing images. If retinal images are artificially stabilized, meaning they're kept from moving on the retina, then the images start to disappear and reappear. Hence, the eye movement allows us to see even while our eyes are fixed by keeping the images moving on the retina. The way you and I are able to measure light is, as we stated earlier, through wavelength, the spectrum that is quite limited with humans, but just enough, and then intensity, on how bright it is. Please note that for wavelength, we rely heavily on colors. And I apologize for, again, the same problem earlier. I try to highlight it for you so you could see that wavelength, again, corresponds to colors, the hues, the different colors that you and I are able to perceive. Which photoreceptor cells do you think are responsive to wavelength, given that you know wavelength corresponds to colors? Whereas for intensity, we'll look at brightness. And for brightness, we would look at the amount of light and the sensitivity that comes in. What photoreceptor cells are responsive to intensity? You may pause the video, think about it. If you answered that wavelength is associated and the photoreceptors that respond to wavelength are cones, you are correct. Remember that cones have a lot to do with color, contrast, and fine detail, acuity, whereas rods have to do with sensitivity of light. And so the right answer for this other one here would be rods, whereas here it would be cones. Once again, transduction is nothing more than a conversion or translation of one form of energy to another. As stated earlier, the brain does not speak light. It doesn't understand light. So in order for us to get the brain to respond to light, we need to convert that message. Picture someone speaking a foreign language to you that you do not understand. If they were telling you that a truck was coming and was going to hit you, but you did not understand what they were saying, chances are you would not be able to move. Perhaps you hear it, but if that's the only language or form of energy that would notify you that a truck was coming your way, it could hit you, you would not be able to respond to that. Same thing with light. Our ability to perceive light, which is the reflection of objects, allows us to see that if there's a threat coming our way, the eyes sense it, they package it, the photoreceptor cells react, send it over through the optic nerve, and it gets sent over to the brain. And the brain then determines whether to activate the muscle so you could move out of the way. Visual transduction is nothing more than conversion of light to neural impulse to neural signals by visual receptors, and that occurs at the retina. At the retina, we actually see an interesting change whenever these photoreceptors are exposed to light. Please note that a pigment is any substance that absorbs light. Pigmentation of our skin can change depending on whether you spend a lot of time out in the sun. If you spend a long time there, depending on the color of your skin, you may turn red or you may get a little bit darker. Same thing with our eyes. If you get a lot of light impacting the eye, there's actually a change in color because the substance actually would absorb light, but contrary to our skin that may take hours or minutes so that we could see a change of it, the change in the color of our rods and our photoreceptor cells would be instantly. Rhodopsin is the biological pigment that's found in our rods. Rhodopsin is basically made up of retinol, which is vitamin A, and that's one of the reasons why optometrists and people tell you to eat carrots, because that's there as well. And it's also combined with opsin protein. Sweet potato, carrots, squash, kale, etc. These are all good vitamin A sources, and they help us improve our vision. People with extreme vitamin A deficiency often suffer from night blindness. This is because it impacts rods, which are responsible for, as we stated earlier, scotopic vision. In our cones, we have another form of protein. That's what we call iodopsin. And there we have basically three colors: blue, green, and red. The blending of these three colors allow us to perceive all the colors. The missing one, or some, or all of these color-specific cones leads to what we call color blindness. Please note that the least common color to be affected of these would be blue. A breakthrough in the study of visual transduction came in 1876 when a red pigment, again is any substance that absorbs light, was extracted from rods. This pigment has had a very curious property. When the pigment, which became known as rhodopsin, was exposed to continuous intense light, it was bleached, meaning it lost its color, and it lost its ability to absorb light. But when it was returned to the dark, it regained both its redness and its light, which basically was its absorbing capacity. Please note that when we are continuously exposed to light, our rods simply become white. They're bleached, and when they lose their color, they're no longer able to absorb light. Does this remind you of a concept we discussed a few slides back? This is the reason why we have these involuntary movements such as saccades, because through the constant repositioning, through the constant movement of the retina, we are able to darken these rods back to where they are, because if they continue to just be bleached, then they cannot absorb light, and if we cannot absorb light, we cannot see. In this picture, we're able to appreciate visual transduction at a rod. You can see that in the dark, when rods are not being stimulated, rhodopsin is basically bound together. Rhodopsin, remember, is that pigment. It has color. By staying bound together, we are able to see and appreciate the color. Think of a stadium. Whenever a stadium has the local team that may wear, say, purple and yellow, and all the fans are there to see this particular team, and then when you look at the seats, it may look like the stadium is all yellow, gold and purple. However, if this team goes away and they're playing away and there aren't that many people wearing gold and purple, then that color would not be perceived by us. It would not be sensed because they're not cluttered together. So remember, when they're bound together, you'd be able to perceive the color. When spread out, you're not able to perceive the color. In the dark, sodium is constantly moving in. Sodium's constantly moving in because the cyclic GMP basically is a regulator of various metabolic processes. This is basically the cyclic guanosine monophosphate. You don't need to know this in here. But this controls how we are able to metabolize whatever's coming in. So whenever we're in the dark, the cyclic GMP, which is this guy right here and this guy, they keep the sodium channels open, and so sodium continuously goes in and out in the cell. However, when we're exposed to light, then there's an activation of the rod, and this brings about what we call an intracellular chemical chain reaction. This should remind you or take you back to chapter 4 where we talk about action potentials. And notice how the cyclic GMP actually causes the sodium channels to close. When there's no more sodium coming in here, then there's a chain reaction. The cell begins to change and form, and the photon of light causes rhodopsin to disintegrate. So whereas rhodopsin was bound together here and we could appreciate its color, when there's no more sodium in, the photon of light then spreads out the color, and this is what brings about the bleaching. This causes a reduction in the cyclic GMP, the sodium channels begin to close, and then we have a change in action potential. When you have action potential, the information is then sent over to the brain through transduction. The brain is able to make sense of whatever the image, whatever the shape, whatever the object is, whether it's static or moving, if it's approaching, if it's threatened, if it's not. The brain then makes an assessment and then activates the body parts if necessary so you can move out of the way.